Hello, seekers. Welcome to the fourth video of blockchain series. So, up until the previous video, we have evolved the design of our solution to the cash recounting problem through multiple steps. In each step, we introduced a design refinement, and most recently, we evolved our design to optimize space, and thereby we arrived at the idea of blockchain, right? Wherein every block has a hash that is a function of the transactions of that block plus the hash of the previous block. With that, we were able to optimize space, make comparisons across nodes far more performant, and if you recall, we also spoke about the idea of how to do a checks and balance across nodes for every node to hold the integrity of the ledger. Every node would constantly do a checks and balance of its ledger with the other ledgers, and anything that is when a node goes offline and when it comes back, and anything that whenever it finds and how it syncs up with the network is it finds the longest ledger, or in other words, the longest blockchain is considered the truth for any node, right? When it comes back online. What we didn't talk about is what if there is a conflict, right? What if what if a node comes back online and it finds that there are two other nodes that both are holding, long blockchain, but their hash values or the latest block is different. Our design, we haven't spoken about the aspect of design that would handle those scenarios, and that's precisely what we're going to tackle here. Right? How are we going to avoid? How are nodes going to avoid conflicts? Right. So let's take a scenario of we have a network which has three nodes, and let's say A and B are two nodes which have the exact same blockchain, and C is the node which went offline and it came back online. And the first thing it'll do, it'll go with the most, it'll go with the longest blockchain. So in this case, both are the same. So let's say that it takes one of them, and it maintains this blockchain. Now, this is something that we've already seen. Now let's take the scenario of C coming back online, and in this case, C observes that the truncated block. The truncated blockchain that it has. The first block is not in sync with any of the other first blocks in the network. So what C does is it once again, it takes the longest blockchain as the truth, and it syncs up with either one of them. Both the other nodes have this exact same blockchain, so it syncs up with 1, 2, and 3. So you might observe that the design so far has allowed us to retain the integrity of the ledger, right? Now let's take this scenario of you have the three nodes, and C has just come back online. It briefly went offline and it came back online, and so which means that it doesn't have the third block yet, but it finds two other nodes, and both the nodes are having the third block on both the nodes are different, right? For whatever reason, maybe there is a this particular node has lost a few transactions, or maybe they've tried to tamper with, or whatever. We'll talk about the idea of tampering later on. But this is possible, right? There can be issues, and you can have the scenario of two nodes having different blockchains, which means that one specific block is different. So now, according to C, both of them are longer are long blockchains, right? Which that C will align with? There are different strategies that we can adopt. The design of blockchain, or the idea of blockchain, or the idea that we are going to pursue here is we will let whenever C undergoes or any node undergoes such a conflict, wherein it's not able to find one long blockchain, but it finds multiple long blockchains, it simply holds both. So C is going to hold both, block 3B and block 3A. Now, after a while, whichever completes first, there are two possibilities that can happen. Either A, builds the next block, or B builds the next block, right? Both are possible. So the moment whichever node builds the next block successfully, so in this case, A builds the next block, which is 4 hash. So once that happens, C would drop the other one, which is block 3B hash, and it will align with this longer. It has clearly got one long chain now, so it takes this as a truth and it maintains this. Now that this has become the truth, now B can also look for syncing up with this long chain, and eventually it will have to it will have to drop this block and then keep this as the longest block here. So as you might see here, over a period of time, it settles down. Over a period of time, the integrity will be held. Although there are brief moments wherein multiple nodes are going to have slightly different blockchains for whatever reason, as long as the majority of the nodes in the network are stable and are able to receive most of the transactions, things will settle down. As long as this approach of a node always considering the longest blockchain in the network as the truth. This strategy will work as long as most of the nodes in the network are stable and honest. Right? When I say honest, because they don't intend to tamper with, and we will actually be proving this as well mathematically in one of the videos later on. But the point I want to make here is that the longest blockchain is the truth, and even if it is one node that has the longest blockchain, the other nodes will sync up with that, and that is how the conflicts are being resolved whenever nodes come back offline, or whenever the checks and balance whenever ledgers don't check out between nodes. It always goes with the longest blockchain, and when there are multiple blockchains of the same length, nodes will hold both, not just two. Even if there are three nodes having three different blockchains of different length, it will hold all the three, and which one of the three is able to create the next block is what will be held, and the other two will be dropped. Right? So that is how we will design that's the design refinement that we will introduce to make it fault tolerant. Now let's move to the next step. So if you observe here in our scenario, we went through scenarios of a node going offline and coming back online, and it syncing up with the longest blockchain, right? And we took the example of node C going offline and coming back online, and when it comes back online, it looks for the longest blockchain, and then it finds whichever is the longest blockchain, and it takes that as a truth, and it proceeds with that, right? Now, for C to be able to do that, you need to have A and B who need to put that effort to build that blockchain, right? There has to be enough nodes in the network to be able to build blockchain so that nodes don't go easy. Nodes don't become lazy. They simply cannot rely on other nodes to maintain the blockchain. Rather, they should also make some effort to build that blockchain. So we need to avoid the scenarios of nodes going in lazy, and the way we can avoid that is by incentivizing these nodes. A node that invests its compute to build a blockchain is incentivized. Through design, we will introduce the idea of incentives, wherein every time a node comes back and successfully builds the blockchain, it gets an incentive in the form of a small credit. So if you might see here, if node C is incentivized, if node C builds a blockchain or builds a specific block and adds that to the blockchain, C will get a credit, a small credit. It can be 1 Bitcoin or some small number, and it can also be a percentage of a transaction, very minute percentage of a transaction. And there are different strategies that you can adopt here. But the point is, nodes needs to be incentivized for the work that they put in for building and maintaining a blockchain here. So as you see here, the specific node, because it is contributed to this particular block, it gets a small incentive here, and in the second block as well, the node C has built it and added to the chain, so it has also got a small incentive. And every node that contributes to the blockchain gets this incentive. So the key here is by design, incentive is built into the design of blockchain, and it is through the idea of incentive that we avoid the scenario of lazy nodes. And blockchain, I mean, and that is what motivates the various nodes to put in their effort and build that blockchain and retain the integrity of the ledger. This is the last thing that we're going to look at, and it's a crucial design consideration for our solution. What are peer reviews in blockchain? So if you really see the whole design construct that we have through the solutions so far from step 1 to 9, what we have enabled is for multiple nodes or multiple devices or multiple smart piggy banks being able to be part of a network, and they can make peer-to-peer transactions with one another. They can print a node A or a device A can create its custom cache, and that can be transacted with device B, and device B can transact with C. And for them to work seamlessly, they'll have to maintain their own ledger, right? Which is a decentralized ledger. Everybody has to know everything about what's going on in that network. And we optimize that design by converting that ledger into blocks and then hashing that block and then chaining it with other blocks. And that's how each of those nodes were maintaining their own independent blockchain. And for this to be completely fault tolerant, and we would need the majority of the nodes to maintain the blockchains well, and that's how we got that incentive of the idea of incentives, so that every node is motivated to build that. Every node is motivated to spend that effort and build that blockchain on its own. So because it is all peer-to-peer, right? It is up to the group to validate one another, whether the other party is doing their job or not, right? Because nodes are incentivized to build that blockchain, and the blockchain is nothing but, it's a hash, right? When we say a node will get an incentive if it is able to create a hash value for that particular block, and which is a function of the hash of the transactions in the block data and plus the hash value of the previous block, right? Now, what stops from a node from faking it? What if a node decides to just give some random value as a hash value instead of actually doing this job? What if the node just gives some random value? We need to have a mechanism to catch those scenarios, right? And what is that? It cannot be. It's not a simple problem, because if node A gives a random hash value to node B cannot simply compare it with its own hash value for a particular block. Although the transactions are, it's going to have the same set of transactions. It cannot just compare it with its own hash value, because there is always a possibility that this node may have lost some transactions because it would have gone offline or so, or it could happen with the other nodes. And we already saw that those occasional missing transactions, that will be balanced. I mean, that will balance out over a period of time as long as the majority is stable. Right? So, but at any point in time, it really cannot 100% confirm that the 100% valid. It cannot validate the transactions of the hash value provided by another node. There has to be a different way to validate this. Now, what we're really trying to validate here is, well, the design allows you this one-off scenarios of missing transactions and all that through consensus mechanisms and all that. It would suffice for a node to just see if the other party who is giving that hash value has actually put in that effort to build that hash value or not. If you are able to validate that, that is good enough. Because if the other party has put in put in that hash value, and if that is significant, the key is, yeah, if that value is significant, then he might as well, spend that effort in preparing this hash for this particular block. So the trick here is to make this problem harder, right? So if preparing this hash value takes 10 compute units, just for an example, if preparing this hash value takes 10 compute units, and if the node that is going to validate this is convinced that this party has put in at least 10 compute units, then that is good enough, because there is no reason, the node that prepares this hash value, even after putting in more effort, it doesn't have to fake or give any random hash value. So the trick here is to make this a harder problem, and we make this harder by the idea of a prefix. We'll come to what this means. But before we talk about this, let's take some examples of how hashing really works. So if you take the string, the grass is green, this is the corresponding hash value for it. Now, if you add a specific, a simple letter like a letter like F to this particular same string, you get a completely different hash value here. And if you add a different letter A, it will come with a different hash value again. But the reason I chose F is, if you include this F and then has this entire value, your hash value is slightly special. It comes with a certain number of leading zeros here. So if you see here, it's a hexadecimal number. So the first value translates to 4 zeros, and the second one translates to 3 zeros and a 1. So this specific, just the virtue of adding a single letter F creates a hash value that has 7 leading prefixes. Now think about this, and you really cannot predict this letter if you want to have a certain number of prefix. Let's say that if you want to have 8 prefix, if you want to have 8 leading zeros, you just cannot easily predict that what is that letter that you need to add. It can be 1 letter or 2 letters or whatsoever, but you just cannot predict unless and until you try them out and hash them out. So the point here is, you take this one, you expect the caller, the person who is giving the block hash value, to also provide you a prefix such that by a hash of that prefix with the hash of the other transaction data and the hash value gives a new hash value which has a certain number of leading zeros. And this is agreed in the network. And for a particular time, everybody agrees that whenever they want to validate their hash value, they are expected to give a new prefix, which can be a string or two, and it can be a string of any length. But the hash value of it has to have that X number of leading zeros. So that X or that N number of leading zeros is agreed by the network. Now, what this makes is that, what this allows is that it makes the problem harder. Now, any node that wants its block to be validated by the other nodes to earn an incentive will also have to solve this problem of identifying this prefix such that the other hash value which is called as a proof of work. So this whole idea is proof of work. Along with the actual work, you're also giving this proof of work, which is actually a harder problem. And unless you give that proof of work, you'll not get that incentive, right? And this proof of work involves identifying this new prefix such that the hash of this prefix plus the hash of the transactions plus the hash value of the previous blocks gives you that leading number of zeros, and which is agreed, that the number of leading zeros is agreed by that network, right? So this identifying this prefix is the hard work that a node has to put in to arrive at this hash, and this can only happen by trial and error. If it is trial and error, it means that it has to expend some compute effort, right? It has to expend some compute. It has to expend some compute time. Now, this is something that every node is expected to provide with, which is called as the proof of work. And unless this proof of work is established, is provided, and it will not be able to earn that incentive. And if you already notice here, to arrive at this prefix, it can only be done through trial and error, but to compute the hash can be done very quickly. So the person who is validating it can do the validation very quickly, as all what he or she needs to have access to is the prefix prepared by the node that wants validation, and the hash of the transaction, and the hash value of the previous block. And it can just run through this hash, and then it can validate whether it has that n number of leading zeros or not. Computing this prefix is a hard problem. Validating this is not a hard problem, right? So we call these problems as NP complete problems, and there is a complete series of work that happens on that ground. And this is how the key thing is you have the proof of work is an integral part of blockchain for nodes to be able to convince the other parties that it has actually spent that much amount of effort to build the blockchain. Thereby, post that validation, it will be able to take that incentive. So I hope with this we have pretty much completed all the key aspects of blockchain, and what we have seen in the video so far is a design that will allow a blockchain to be technically sound in handling transactions and maintaining these transactions. And just to summarize, we started with a peer-to-peer transaction mechanism through a smart piggy bank. We then introduced the idea of a transaction log, a decentralized transaction log. We evolved that into a public ledger, which also had the wallet value. And then we made it more secure by introducing new private key pair per transaction, the idea of a one-time PIN and all that. And we also addressed the privacy concerns through pseudonames. And then we also saw how we make it fault tolerant by through the consensus protocol, wherein the majority wins, as well as the longest chain is what is going to be the truth, right? And we also optimize the whole process of storage space through the idea of blockchain, wherein the blockchain is the hash of the transactions and the previous blockchain values, and which makes it obviously immutable, because you are working on hashes, and which means that you have a flexibility of clearing off or stubbing of the actual transaction data without losing the integrity of the ledger. So which makes the whole blockchain immutable and an append-only system. And we also saw the idea of incentives, how the nodes are incentivized to not just do catch-up work, but also to actually do the blockchain work, to build the blockchain, which means that they'll get an incentive. And they'll get an incentive only when they're able to provide a proof of work, not just the actual work or the hash, but they should also do that proof of work, which means that they'll have to solve this harder problem of identifying that prefix, which gives that new hash value, which has that specified leading number of zeros. So I hope these sessions were helpful. We are still not through. There are a few more videos coming up, and wherein we will show the security. We'll prove what we have done so far is we have through technical design considerations, we were able to convince or articulate that how the system can be foolproof. But in the next videos, we will prove that mathematically too, right? And that's also pretty interesting work, and we'll go through all possible details in that. Thank you.
If you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.